The specific volume is also a big number, so I mean that n over v is a big number. N over v is a really big number. The particle here, I mean the electrons, the proton or photon and everything, they have several types of the interactions. The easiest interactions which the particle have is due to the charge. They can have the charge. So they have electromagnetic interaction. Also, if in some sense you can consider the gravitational force on the particle, but that's very negligible. So gravity normally is considered very negligible. But electromagnetic interactions are very important because they are basically some charged particles like plus, minus. By E I mean any other particle, it's not only electron, it can be any particle like with the positive charge. So they have a electrostatic or electromagnetic interactions because they are moving. And this is, I want just to tell you how much the difficulty we have. Except the electrostatic potential between two charges, the Coulomb. I mean the Coulomb interactions. You have a Coulomb interaction, which is given by the two particles. You have this type of the interaction. K is the Coulomb, so Qi Qj over Rij. This is a Coulomb interaction. Except that when the charges are moving, so you can have a little bit magnetic field also. And you can detect that magnetic field if the size of the system is very tiny, even if it's very tiny. So you can have a magnetic field. So that interaction will be electromagnetic interactions. So, and the other problem is that not only this simple type of the interactions, there are mutual interactions between the particles. So each particle make interaction with the other one. So this is all the, if you can include all of this type of the interactions, you can get the potential energy. But that's very hard. So for that reason, we just consider the ideal systems. At the first approximation, we forget about the interactions. And then in the next step, you need to consider the interactions. But there is the situation is more complicated because, as I explained in the first lecture, you needed to use the quantum mechanics. So actually, basically, you are required to solve the Schrödinger equation with such potential. So just imagine that's impossible to solve that exactly. So you needed to use the approximation. And there are some methods like cluster expansion and some things, advanced methods, which they use the potential in their calculations. But basically, in our course, we will consider the potential just very softly and not very strong potentials. So, and we will consider the potential as the effect to the ideal systems. But that will become like a perturbation to our system. So about the work, there are a lot of words we can write that. Before to explain you that the difference between the work and the heat, because they both are written in the differential form, but they are basically in the differential form. They will be very completely different. One of them will appear as a total differential. Total differential. I will explain you the basic math. And the other one is incomplete. Incomplete differential operator.
You mean partial?
No, it's in different. I will tell you that. One of them is exactly the gradient of some functions. So if you find a function and take it the derivative, I mean the total derivative, you can get the derivative. But the other one, no. The other one, it depends to the process. I mean, to find the delta Q, you need to exactly know that which type of the process your gas is going. In which direction or in which process the gas is moving. But the other one is independent from the process. Do you remember anything about the classical mechanics? You know, the work in classical mechanics is F dot dr or dx Ax is the displacement. Yeah. And F is the force. For conservative systems, when you have the conservation of the energy, the total, yes, the F can be written in terms of the gradient of the sum type of the potential. I write very generally. So normally it will be a function of just one or two parameters, but generally speaking it can be a function of the 3 dimensions. So this is, it gives you that the total value will be integral of f dot dx. And look at that, what is happening is that d phi, the gradient phi dot dx. And if you remember a little bit from the math, gradient phi dot dx is partial derivative of this, partial derivative of this, partial derivative of this, multiplied to a vector with the infinitesimal component. So that will be the total derivative by chain rule, by the magic chain rule. That will be just d phi. This is the d phi, the definition of total differential. And look at that. So gradient phi dot dx will be total derivative. So this is the total derivative. So basically the w will be minus integral d phi from the initial to the final. It could be coordinate, it could be anything, any other parameter you have it. But finally it will be given as that, minus delta phi. And for conservative system, it's independent from the process. Huh? I mean, it depends just to initial and final state of your system. It doesn't depend that how the gas pass and which approach it passes and reach the point F when it started from the air. So that's about the force. That's about the work, mechanical work actually. If you wanted to use this equation in thermodynamics, by some way, we needed to define a quantity called pressure. And we defined the pressure like force over the area if this is your system. So you choose a part of the system, and I hope you understood that from the physics too. The area is a vector. When you want to find the flux, Gauss electromagnetic flux, you needed to consider delta A as a vector. So this is a vector. But there is a problem here. What about the F? F is vector also, huh? Yes, F definitely is a vector because it follows the vector rules. So you have something like that. I don't know, this is the delta F. And we define pressure as a change of the rate of the change of the force versus the area. What does it mean that you are divided a vector by the vector? What does it mean? Can you do that? Can you do that? Can you divide the vector by the vector?
It should be. Yes, it will. Yes, it will give scalar.
Not always. Not always. If they are in the same direction, opposite or parallel or unparallel, it will be number, huh? But tell me that if the vector is like that and delta A is like that, how you can divide these two? The divide of the delta F to delta A is not number. Generally, it's not a scalar. It's a quantity called a tensor, but we are not very much going to that. That is like the matrix, but very different to the matrix. But generally speaking, the pressure is a tensor. A 3 multiplied to the 3 matrix. So this is the pressure, basically. Pressure is not the number. But for our business, we just restrict ourselves to the simple definition of that, and we say that the thermodynamic pressure, thermodynamic pressure, we define that as the magnitude of the vector over the magnitude of the A vector, and taking the limit and the times delta x. And from here you can substitute f, or the magnitude of the f, from this equation. So you will get delta W will be, instead of the f you put a p delta A delta x. But be very careful to writing this equation like that. You need to write like that. What does it mean delta A delta x? I know that this notation is not correctly because we needed to write the p as a tensor. Otherwise, as a mathematical physics person, I don't very much love this equation. Here you have a vector. So something should be here to cancel this vector form. So it will be matrix, or as I called you, tensor. So it should have two index. Vector has just one index, like x, y, z component. It has just one component, x, y, z. So it should have two components, x, y, x, 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 z, or z. Anyway, we write very non-technical this equation. So what does it mean delta A delta x? So it means that you change your system very slowly and keep it the form of delta A, but move the system in the direction of the x, just a little bit infinitesimal distance. So what you will see is that you will see that the change in the volume in the space, and this is called delta V, Delta V, the volume change, is formally written delta A delta x. I know that this is not very correctly written. It should be some integral or something, definitely. I can approximately write that. So by this non-technical writing, we can write the work, the thermodynamical work, as a simple expression in terms of the pressure. So delta W for our business of thermodynamic is proportional to P delta V This is some type of the energy, This is some kind of the energy. This is the force which exerts to the system. So if you want to move the system, you needed the force exactly same as F, but in the opposite direction. Yes? So you needed to...
So minus sign.
If you understand this statement, is okay. Otherwise, I'm not very happy about this statement. What I understood is that in physics, all the phenomena, all the systems are moving from the higher potential to the lower level potential. Yeah?
Yes.
Water never falls down from the bottom to the top. The water is falling from the top. So from the maximum potential, so if I call a phi as a potential, to the minimum potential. So that flow direction is the reason that I needed to put the minus here. So that's it. Because delta W is proportional to the change of the energy. So change of the energy is going from the maximum to the minimum. So I put this here to guarantee this, to remember that. So there are many ways to interpret this equation. So this is the first law of thermodynamics. So, and about the delta Q, I want to tell you that delta Q is very problematic. Delta Q can be written in the simple equation T delta S. T is the temperature, as I explained to you, is related to the average of the kinetic energy. And delta S is the entropy. So this is the one of the reasons that the statistical physics developed is to find a reason to explain the entropy. Because there is no easy way to explain the entropy. We don't have any much more sense about the meaning of the entropy. Just what we know that the entropy is related to the number of accessible state of the system. If you have 20 positions or any other, not 20, I made 12. If you have a 12 position and you have 11 people want to sit in this small room, the number of the people are 11 people, and the number of the seat is 12, okay? They want to enter a small room with just 12 seat, 11 people, and want to sit at that. I know that they will have a difficulty, yes? They need to say, excuse me, and then pass on the seat, yes? If the room is very small, huh? I mean, when you will see the final arrangement of the system, it will take time for you, huh? You need to wait till everybody settle in the system, in the sitting. But look at that, 11 people want to start to sit it in the big hall. So final arrangement takes time, huh? Takes time. But if 11 people want to sit in the hall, that this is around 500 seats. 500 seats. So you have more possibility, more accessible state. It should not be like that. Everybody can go and sit. So the final state, the final arrangement, the system reach final arrangement quickly than case 1, case A. This is what we case A, and this is a case B. But of course, their sitting will be very randomly. One will sit in the first, and one will sit. Anybody will sit in any place which is more close to him or more comfortable. The accessible states, the number of accessible states, which we show the omega. Omega is the number of the accessible state. It is directly related to the concept of the entropy. The distribution of the particle in such big hall is very randomly, Maybe the 2 persons will sit in and 2 will sit in the other place, very far from that. This is what is happening in the big hall. Or if they are electron, and if there is a position like that, not electron, any other particle, because electrons have some conflict with each other according to the Pauli exclusion principle. Anyway, if you just forget about the people and think about the electron, and if you consider the seat like the energy state, the possibility of the energy, if you have a small number of the possibility, or if you have a small number of the energy level, reaching the final arrangement takes more than time that if you have many accessibility. Equilibrium. This final arrangement, we call it equilibrium state. When all this movement finish and when you see the final picture of the system. Equilibrium. So I make a very important statement here that attending equilibrium state is more easier in systems with large number of accessible state or possibility. Our statistical mechanics is only about the equilibrium. The statistical mechanics for unequilibrium state is very different from the equilibrium thing. But we are talking about the equilibrium. So entropy is related exactly to this. Entropy is related to the number of the accessible states.